NASA already changed the path of an asteroid, not in a movie, not in a simulation, but in real space. For the first time, humanity proved it could nudge a small world off its course. But if a much larger asteroid were truly heading for Earth, would that be enough to save the planet? Or was DART only the first tiny step in a much bigger fight? If this kind of deep space science fascinates, please like the video, subscribe to the channel, and settle in. The solar system appears calm when seen from far away. The Sun holds almost all of its mass at the centre, and the planets travel around it in long, repeated paths that seem orderly, from one season to the next and from one century to the next. Yet this order is not empty. Between and beyond the planets, countless smaller bodies move through the same field of gravity. Some are asteroids, bodies made mostly of rock or metal. Others are comets, bodies that carry large amounts of ice mixed with dust and darker rocky material. They are not strangers that arrive from nowhere. They are part of the solar system itself, shaped by the same beginning and still moving under the same rules. These smaller bodies remain from the early making of the solar system about 4,600,000,000 years ago. In that early time, gas and dust circle the young sun in a broad disk. Tiny grains meet, cling, and grow. Some become planetesimal, meaning early building blocks of planets. A small number continue to grow into the major worlds. Many others do not complete that journey. They are broken, scattered, heated, cooled, and rearranged. Some are pulled into larger bodies. Some collide and shatter. Some remain in long-lived populations that still circle the sun today. Their existence shows that planet formation is not a neat act with no residue. It leaves fragments on many scales, from dust to mountains of stone. The largest concentration of rocky bodies lies between the paths of Mars and Jupiter. This region is often called the main asteroid belt, but it is not a crowded wall of rock. It is a vast volume of space, and the bodies within it are usually separated by immense distances. What makes the belt important is not visual density but shared history. Many asteroids there are remnants of material that does not gather into a planet. Jupiter's strong gravity helps keep that from happening. Its repeated pull stirs the region and raises speeds enough that collisions often break bodies apart instead of letting them merge gently. The belt therefore remains a record of incomplete assembly. Beyond the giant planets, other reservoirs continue the story. Past Neptune, a broad population of icy bodies circles in the cold outer darkness. This region, commonly called the Kuiper Belt, contains objects that preserve material from the distant early disk. Farther still, on paths so long that one circuit around the Sun may take immense spans of time, a much more distant cloud of icy bodies is thought to surround the solar system. This cloud is understood through the arrival of long-period comets, whose paths point back to a remote source. Together, these outer populations show that the solar system extends far beyond the familiar paths of the major planets, and remains full of leftover matter in slow, continual motion. None of these regions is perfectly sealed. Gravity keeps every body on a path, but those paths are not always permanent. Small repeated nudges matter. A close pass by a planet can alter direction and speed. A collision can create fragments with new orbits. Even sunlight can slowly change an asteroid's motion over very long times, when absorbed energy is later released as heat. This effect is small at any one moment, yet over many years it can shift an orbit enough to matter. In a system that lasts for billions of years, even weak influences accumulate. The result is a solar system that remains active, not through constant violence everywhere, but through unending gradual rearrangement. Because of this, asteroids and comets do not stay fixed in one class of path forever. Some asteroids move in stable families for ages. Some drift into resonances, which are orbital patterns linked to the repeated pull of a planet, especially Jupiter. In a resonance, timing matters. A body receives small gravitational tugs again and again in a way that can enlarge changes over time. This may stretch its orbit, tilt it, or shift where it travels. In this way, material from the main belt can be guided out of its older home and sent inward. Comets also change. As they approach the Sun, ice warms, gas escapes, and jets of material leave the surface. That loss can slightly alter motion while giant planets continue to redirect them with their gravity. The inner solar system is where these changing paths become especially important. Here the 4 rocky planets circle closer together, and space contains more opportunities for crossing routes. A body whose elongated orbit now reaches inward may pass through the orbital distance of one planet and then another. At this stage it may be described as a near-Earth object if its orbit brings it into the neighbourhood of Earth's path around the Sun. Most such objects are asteroids, though some are comets. The term does not mean immediate danger, it simply describes an orbit. A body may come near Earth's orbital distance while Earth itself is elsewhere along its path. Space is large, and timing decides whether 2 bodies merely share a region or arrive at the same place at the same time. This wide orbital picture explains why impacts are possible without making them mysterious. No special force sends a threatening object toward the inner planets. Ordinary mechanics is enough. A fragment remains from the solar system's formation, spends long ages in one reservoir, drifts under subtle forces, receives repeated nudges from planets, and adopts a new path that crosses the routes of worlds closer to the Sun. The same laws that keep the planets in stable motion also allow some smaller bodies to wander across those planetary lanes. Nothing in this process is hurried. It unfolds across spans of time far longer than a human life, yet it never truly stops. Seen from this outer scale, planetary defense begins as an issue of celestial traffic rather than drama. The solar system contains many populations of small bodies, each with its own materials, distances, and orbital habits. Rocky asteroids dominate many of the near-Earth paths, while icy comets may arrive from much farther away with very different histories and sometimes with less warning. Some bodies are single, solid masses. Others are loose collections of rubble held together mainly by weak gravity. Some turn slowly, some tumble. Earth is not isolated, and the space around the Sun is not empty. It is a structured moving environment filled with ancient debris that continues to travel, drift, and occasionally cross the paths of planets under the steady rule of gravity alone. Earth moves through the solar system on its own quiet path around the Sun. From the ground, that motion is not felt. Seas rise and fall, winds cross land, clouds gather and clear, and the planet seems steady beneath every daily activity. Yet Earth is never still. It travels around the Sun at great speed while turning on its axis, and it does so inside the same gravitational setting that guides planets. Asteroids, comets, dust, and fragments of rock. Because Earth is one body among many in motion, it is not simply a place that waits. It is a moving target, following a fixed lane through a region where other bodies may pass, drift, or cross. This makes impacts part of ordinary planetary life. Earth does not need to seek danger. It only needs to remain in a system where old debris still exists. Every year, small particles from space meet the upper atmosphere. Most burn away as brief streaks of light. These are tiny pieces, often no larger than grains or pebbles, and they usually vanish high above the ground. Their harmless disappearance can make the larger truth easy to miss. Earth is continually meeting material from space. The atmosphere hides much of that contact, but it does not erase the fact of contact itself. The planet moves through a stream of natural leftovers, and the stream does not end. The atmosphere is one form of protection, but it is not a perfect shield against all sizes of incoming objects. A very small particle slows, heats, and breaks apart quickly. A larger stone may survive long enough to scatter fragments over land. A larger body still may reach the surface with great force. The outcome depends on size, speed, angle, strength, and composition. A dense iron-rich object behaves differently from a fragile stony one. A loose icy body behaves differently again. Earth therefore does not experience a single kind of impact. It experiences a spectrum, from invisible dust settling through the air to rare collisions that release energy on a scale large enough to mark geology and history. The Moon preserves a simple, visible record of this process. Its surface remains covered with craters because it has no thick atmosphere, no rain, no rivers, and no active surface weather like Earth's. Marks made long ago can remain for immense spans of time. Earth is different. Wind wears rock down. Water cuts valleys and fills them with sediment. Ice grinds and reshapes the surface. Volcanoes cover older ground with newer material. Tectonic plates, the large moving slabs of Earth's outer shell, sink, rise, and recycle crust over very long intervals. Because of this continual renewal, Earth does not preserve every scar. The surface forgets much of what happens to it. Yet the forgetting is only partial. Some craters remain. Some impact layers survive in rock. Some traces stay locked in minerals and sediments, waiting to be studied. This means Earth's impact history is deeper than casual sight suggests. The absence of visible fresh craters in most landscapes does not mean a quiet past. It means the planet is active enough to erase or bury many old records. When geologists examine ancient layers, shocked minerals, impact melt, microscopic spheres of cooled debris, and unusual chemical signatures reveal that large collisions do occur. They are uncommon on human timescales, but they are normal on planetary timescales. Earth exists for more than 4 billion years, and across that span even rare events become part of expected history. Impacts help shape worlds in more than one way. In the earliest era of planet formation, collisions are central to growth itself. Small bodies strike one another and combine. Young planets gather mass through repeated impacts. Earth's own distant past includes giant collisions that help determine its structure and its surroundings. Later, once the main planets are established, impacts remain agents of change rather than growth. They excavate craters, melt rock, throw dust and stone into the air, disturb climate, ignite fires in some cases, and send waves through land and sea. The exact effects depend on where a body arrives, what it is made of, and how large it is. A strike into the ocean differs from a strike into continental rock. A small airburst differs from a surface impact. No single image captures all events. What remains constant is the geometry of exposure. Earth presents a cross-section in space simply by existing as a large body in motion. Gravity also enlarges that effective target. An incoming object that passes near Earth may be bent inward by Earth's gravitational pull. This process, called gravitational focusing, increases the chance of collision beyond simple straight-line geometry. The atmosphere then adds another layer of selection, removing many small bodies before they can strike the ground. Together, size, gravity, and atmosphere determine how Earth meets incoming material. The planet is both exposed and defended at the same time. Life develops under these conditions, not apart from them. For most of human history, the sky appears stable and separate from daily survival. Falling stones seem rare, and large impacts rarer still. Yet the geological record shows that Earth's surface environment is never completely sealed from the rest of the solar system. On long enough timescales, external events matter. They can alter regional landscapes or, in extreme cases, contribute to global environmental change. Observations indicate that one major impact near the end of the age of dinosaurs is associated with severe worldwide disruption. It remains clear that impacts belong to the same planetary story as climate, volcanism, oceans, and plate motion. They are not outside nature. They are one of its intermittent forces. Earth therefore occupies a special position in this subject. It is neither helpless nor immune. Its atmosphere removes countless small threats each day. Its size and gravity give it stability as a world, yet also make it a body that can capture incoming objects. Its active geology hides much of the ancient record, yet not enough to conceal the overall pattern. Most importantly, Earth carries a biosphere and a civilization on its surface. A collision that would be only a crater on an airless world may become a disaster here because oceans, air, ecosystems, cities, and human infrastructure all respond to sudden energy release. The same event has different meaning on a lifeless rock and on a living planet. At this scale, before any telescope begins its search, and before any spacecraft leaves the ground. The basic truth is simple. Earth lives within an old and busy solar system. It travels through regions where leftover bodies still move. Most pass harmlessly. Some arrive as light in the sky. A few are large enough to matter greatly. Impacts are not signs that nature has failed. They are signs that Earth remains part of the larger celestial environment from which it forms and within which it still moves. The near-Earth sky does not announce itself as dangerous. It looks like the same broad darkness that has always stretched above fields, coastlines, deserts, and cities. Stars appear fixed from night to night. Planets move with patient regularity, and the deeper background seems quiet. Yet within that quiet field, small bodies travel on paths that may bring them near Earth's orbit. Most are faint. Many reflect little sunlight. Some remain visible only for short intervals before distance, glare, or geometry hide them again. Because of this, planetary defense begins not with force but with seeing. It depends first on learning how to notice a moving object against an immense background that is mostly still. This work belongs to surveys, meaning organized observing programs that repeatedly scan wide areas of the sky. A single observer can discover an asteroid, and historically many were first seen by individuals or small teams. Modern planetary defense, however, depends on persistence across large sky areas and over many nights. The task is not merely to look once. It is to look again and again, comparing images so that a small shifting point can be separated from the far more numerous stars and galaxies that remain fixed. The challenge is practical and mathematical at the same time. The sky is large, the objects are faint, and the motion may be subtle over short periods. Most near-Earth asteroids are discovered with optical telescopes. These instruments collect visible light, allowing cameras to record many sources at once. A survey telescope typically images one part of the sky, then another, then returns to the earlier field after a short interval, when software compares the frames. The fixed stars remain aligned while a nearby asteroid has shifted slightly. This small change is enough to mark it as a moving object. In simple terms, the search is a search for motion. Brightness matters because faint objects are harder to record, but movement across repeated images is what reveals that a point of light belongs to the solar system, rather than the deeper universe beyond it. The observing conditions matter greatly. Dark skies help, though modern surveys also rely on sensitive detectors and careful image processing. Clear air matters because clouds scatter and block light. The height of an object above the horizon matters because low objects are seen through more atmosphere and often appear dimmer and less sharp. The phase of the moon matters because moonlight brightens the sky. The position of the sun matters as well, because bodies approaching from the sunward direction can hide in glare and remain hard to detect from the ground. This is one reason why no search system is complete. There are always regions of the sky that are temporarily difficult to examine. Time also shapes the search. An asteroid may be easiest to detect only during a narrow window, when it's both near enough and in a dark part of the sky. Before that moment, it may be too faint. Afterward, it may move away or sink into bright twilight. Some objects are found years before a close pass. Others are found only shortly before they come nearest. The outcome depends on their size, reflectivity, orbit, and observing geometry. A dark object reflects little sunlight and may remain hidden longer than a brighter one of similar size. A small object can be nearby and still difficult to see. A large object far away may be easy to detect, while a much smaller one close by may escape notice until late. For this reason, planetary defense relies on networks rather than isolated instruments. Different observatories in different locations help fill gaps left by weather, season, and daylight. One telescope may discover a candidate, while others quickly try to confirm it. Confirmation is essential because a single brief detection is not enough to establish a reliable moving object. The same body must be seen again. Its position must be measured carefully against known stars. Further sightings help determine whether the first point of light is a real asteroid, an image defect, or some other transient event. This repeated checking turns a possible discovery into a tracked object. Computers play a central role in this work. Modern detectors produce large volumes of images, far more than any individual could examine point by point with the needed speed. Software identifies points of light, removes many false signals, links detections across short time intervals, and proposes candidate tracks. Human judgment still matters, especially in verification, calibration, and interpretation. But the first sorting now depends heavily on automated systems. In practice, the search for hazardous asteroids is a partnership between optics, electronics, software, and patient-repeated observation. Some surveys use infrared light rather than visible light. Infrared instruments detect heat, which can help reveal dark bodies that do not reflect much sunlight. This is especially useful because an asteroid's apparent brightness in visible light depends not only on size, but also on how reflective its surface is. A relatively dark object can look smaller than it truly is if judged by visible light alone. Infrared observations provide a different kind of information, helping scientists estimate size more accurately when combined with visible measurements. In planetary defense, this matters because physical size is closely tied to the possible severity of an impact. The results of these surveys do not remain at the telescope. Observations are sent to central collection systems where positions and times are archived, checked, and distributed. There, individual sightings from different observatories can be combined into a common record. This shared structure allows astronomers around the world to respond quickly when a newly found object needs more attention. It also means that planetary defense is international by nature. The sky is shared, and an asteroid does not belong to one nation's horizon alone. Discovery, confirmation, and continued tracking depend on cooperation across institutions and borders. Even with this effort, the search remains incomplete. Small asteroids are numerous. Many are too faint except at close range. Some parts of the sky are repeatedly hard to cover because of sunlight or seasonal limits. Observatories on Earth cannot watch through clouds or daylight. Instruments age, schedules compete, and the sky changes continuously. Yet incompleteness does not make the effort weak. It defines its purpose. Surveys steadily increase the known population of near-Earth objects, improve the catalogue of orbits, and reduce the chance that a large threatening body remains entirely unseen. The work is cumulative. Each night adds measurements, and each measurement helps turn an unknown sky into a more measured one. At this stage of the subject, before any orbit is refined into a future close approach and before any threat is weighed in detail, the essential act is still simple. Telescopes return to the sky. Cameras record the faint light of moving bodies. Observers and software separate motion from stillness. Networks confirm what one instrument first notices. In this way, the near-Earth sky becomes less a place of hidden surprises and more a field of objects that can be found, named, and followed. A newly discovered asteroid is not known at once in the full and settled sense of the word. At first, it is only a small moving point recorded at a few specific moments against the much more distant background of stars. Those moments matter because motion in space can be reconstructed from position and time. Yet the first record is always limited. It covers only a short arc of the object's path, perhaps over part of one night or across a few nights. From that narrow glimpse, astronomers can estimate an orbit, but the estimate still carries uncertainty. The asteroid is real and its motion is measurable, though its future path remains surrounded by a zone of possible solutions rather than a single exact line. This is why repeated observation is essential. Each new sighting adds another anchor point. When the object is measured again at a later time, some possible orbits no longer fit the data and fall away. The remaining solutions become fewer and closer together. In simple terms, uncertainty shrinks because the asteroid has had more time to reveal how it actually moves. A line drawn from only 2 or 3 points may fit in many ways. A longer chain of points forces the path into a more precise form. Astronomy therefore moves from detection to orbit determination through patience and return. The sky is watched again. The object is found again, and each recovery turns possibility into constraint. The orbit itself is not a simple circle in most cases. Asteroids travel around the Sun on ellipses, meaning paths that may be nearly round or noticeably stretched. Their orbits also have tilt relative to Earth's orbit, and the direction of that tilt matters. To describe one orbit fully, astronomers use a set of orbital elements, which are the numbers that define size, shape, orientation, and place along the path at a given time. These numbers are not chosen freely. They are derived from observation, and then refined as more measurements arrive. Once an orbit is known well enough, the object's future positions can be predicted with increasing confidence over specific spans of time. That confidence, however, is never created by sight alone. It depends on careful measurement. Each image must be calibrated so that the asteroid's position can be tied accurately to the star field around it. Star catalogues provide reference positions, and modern measurement reaches high precision because the background frame is known so well. Still, every observation carries small errors. The air shifts light slightly. Instruments have limits. Timing must be exact. A faint object may be measured less precisely than a bright one. Orbit determination therefore uses not one perfect point but many imperfect ones combined statistically. The goal is not to pretend error does not exist. It is to model it honestly and allow repeated data to reduce its effect. From this process comes the idea of an uncertainty region. Instead of imagining the asteroid as fixed at one mathematically exact place, astronomers represent the present knowledge as a cloud of nearby possibilities consistent with the observations. As more data arrive, this cloud narrows. When projected into the future, the cloud becomes a corridor along the asteroid's expected path. A close approach to Earth is then studied not as a dramatic single line crossing another, but as an encounter between Earth's position and that corridor of possible future positions. If the corridor passes far from Earth, concern decreases. If it overlaps Earth's future location, more observation becomes urgent, not because impact is certain, but because knowledge is still incomplete. This makes time a central partner in orbit refinement. Some asteroids are observed through one apparition, meaning one interval when geometry and brightness make them visible from Earth. Then they are lost in sunlight or distance for months or years. When they return and are recovered again, the longer baseline greatly strengthens the orbit. It is as though the solar system itself provides a second test. A predicted position is calculated in advance. If the asteroid appears near that place when it becomes visible again, confidence rises sharply. If it appears elsewhere, the earlier solution is corrected. Recovery across long intervals is therefore one of the most powerful ways to turn a tentative orbit into a stable one. In some cases, older images become newly valuable. After an asteroid is discovered, astronomers search archival data to see whether it was accidentally recorded before anyone recognized it. This process is often called precovery because it extends the observation record backward in time. A single earlier image, properly measured, can lengthen the known arc of motion by months or even years. That longer arc may improve the orbit far more than many closely spaced observations from one short period. In this way, the past can strengthen the future. The asteroid has already crossed the camera's field. Only later does human attention return and draw out the significance. Planetary close approaches also complicate the picture. When an asteroid passes near a planet, especially a large one, gravity can slightly or strongly alter its future path. This means long-term prediction is not always a matter of extending one unchanged orbit indefinitely. The solar system is dynamic. Earth, Venus, Mars, and especially Jupiter continue to perturb smaller bodies, shifting their motion by small amounts that accumulate or by large amounts during closer encounters. For most objects and for moderate spans of time, orbital prediction works very well. Over longer intervals, uncertainty can grow again because small present errors and later gravitational nudges spread out into wider future possibilities. Orbit determination is therefore not a single solved act but an ongoing process of maintenance. For some asteroids, subtle non-gravitational effects also matter. Sunlight warms a rotating body, and the delayed release of that heat can create a minute force. Over long times, that tiny push changes the orbit enough to become measurable. Scientists account for this when the data are good enough, especially for smaller bodies where the effect is more noticeable. This refinement shows how precise the work can become. Even a weak thermal recoil, almost meaningless over a day, can matter over years and decades when predicting where an asteroid will be during a future close pass. Out of all this comes a calmer and more exact understanding of near-Earth motion. A new asteroid begins as a faint moving point. It becomes a set of measured positions. Those positions become a provisional orbit. repeated observations, archival recoveries, careful calibration, and mathematical fitting reduce the uncertainty. Future close approaches then emerge not as guesses but as computed encounters with known margins of error. What begins as a brief sighting in the night sky becomes, through disciplined repetition, a path that can be followed far ahead in time. Finding an asteroid and calculating its path do not by themselves explain what it means for Earth. Motion tells where a body may go, but danger depends on more than its orbit alone. Scientists therefore judge a possible threat by combining several kinds of knowledge. They look at how large the body's likely to be, how fast it would be moving if it met Earth, what it is made of, how strongly it holds together, the angle at which it might enter the atmosphere, where that encounter might occur, and how much warning time exists before the event. A threat is not measured by fear or by appearance in the sky. It is measured by physical consequences. Size is one of the first and most important factors. A very small object can make a bright streak and vanish harmlessly. A somewhat larger one may produce an airburst, meaning an explosion in the atmosphere caused by rapid breakup and deceleration before the body reaches the ground. A larger one may survive farther downward and scatter fragments or strike the surface directly. A much larger body can excavate a crater, send debris high into the air, and disturb land, ocean, or atmosphere over wide distances. In general, larger bodies carry more mass, and at a given speed more mass means more energy. Yet size is not always known immediately from discovery alone. This uncertainty begins with brightness. When astronomers first detect an asteroid, they usually see only reflected sunlight. A bright object may be large, but it may also simply have a reflective surface. A dark object may look modest while actually being much larger. To judge hazard well, scientists therefore try to estimate not only apparent brightness, but also reflectivity, which is the fraction of light a surface reflects. Infrared observations are valuable here because they help reveal how much heat the body emits. With visible and infrared data together, size estimates improve. Until then, the same point of light may allow more than one physical interpretation. Speed is the next essential factor. An asteroid meeting Earth is not merely falling downward like a stone released from a hand. It already travels around the Sun, and Earth travels as well. The encounter's speed depends on both motions and on the geometry of the crossing. A body approaching on a steeply different path can strike at much greater speed than one moving on a more similar orbit. Because impact energy rises rapidly with speed, even a modest object can become far more damaging if it arrives fast. This is why hazard assessment always treats motion and mass together. A large slow object and a smaller fast one do not create the same outcome, yet neither can be judged from size alone. Composition matters because materials respond differently under pressure and heat. A dense iron-rich body can stay intact longer as it pushes into the atmosphere. A stony body may fracture sooner. A loose rubble pile object, meaning a collection of pieces held together mainly by weak gravity, may begin to separate earlier still. Comets or icy bodies behave differently again because volatile material can escape and weaken the structure as heating rises. The important point is that the atmosphere does not act on every incoming body in the same way. Two objects of similar size can produce very different events if one remains coherent while the other breaks apart at high altitude. Strength is related to composition but not identical to it. An asteroid may be made of stone yet still be highly fractured from ancient collisions. Another may contain metal and rock but hold together more strongly. Internal cracks, porosity, which means empty space within the material, and past damage all affect how the body behaves. Scientists often begin hazard analysis with imperfect knowledge of these properties. Observations indicate general classes, but it remains uncertain for many objects exactly how they would fragment under the immense stress of atmospheric entry or a surface collision. This uncertainty does not prevent assessment. It means that good assessment includes a range of outcomes rather than a single rigid prediction. The angle of entry also changes the result. A body arriving steeply passes through the atmosphere more directly. One arriving at a shallower angle travels through more air before reaching lower altitude. A longer atmospheric path gives more time for heating and breakup. That can reduce ground damage in some cases, though not always in a simple way. A shallow entry can also spread effects across a longer region. Hazard is therefore shaped not just by what arrives, but by how it arrives. The same object meeting Earth under different angles may generate a different balance of airburst, fragmentation, shock wave, and ground impact. Location matters once the path intersects Earth. An impact over open ocean differs from one over land. A strike in a remote region differs from one near dense population. A burst high in the atmosphere above a city may cause broken glass and structural damage over a large area even without a crater. A surface impact into rock, soil, or sea transfers energy in different ways. For this reason, scientists separate physical hazard from human consequence. Physical hazard describes the event itself. Human consequence depends on exposure, meaning how many people, structures, and systems lie within reach of the effects. A moderate event in an empty region can remain mainly a scientific event. A similar one over inhabited ground can become a disaster. Warning time changes almost everything. If an object is found many years before a possible impact, astronomers can improve the orbit, narrow uncertainty, and judge the hazard with much greater confidence. Emergency planners can also study where effects may occur and consider practical responses. If discovery comes only days before arrival, even a small uncertainty in position matters greatly, and the range of useful response becomes much narrower. This is why scientists do not speak of hazard as a single fixed number. They speak of a developing picture that becomes clearer as more observation accumulates. Time is part of the threat itself, because time determines how much can be known before the event and how much uncertainty can be removed. To help communicate this changing picture, astronomers use formal scales that combine probability and consequence into a simpler public description. These scales do not replace detailed analysis, they summarize it. A low rating does not mean the object is harmless in every sense. It means current calculations show either a very small chance of impact or consequences too limited to justify great concern. A higher rating reflects greater need for attention, either because the probability is higher, the object is larger, or both. These systems are useful because they keep judgment tied to evidence instead of alarm. Threat assessment, therefore, turns raw observation into practical meaning. A moving point becomes an estimated size, a likely composition, an expected speed, a possible entry geometry, and a set of consequences that range from negligible to severe. Some uncertainties remain, especially early on, yet the process itself is steady and disciplined. It asks not whether a discovered asteroid sounds frightening, but what the laws of motion, material behavior, atmosphere, and exposure actually imply for Earth. Once a possible impact becomes a matter of real calculation rather than distant possibility, the subject changes from observation to response. At that point, planetary defense means the set of ways by which human beings may reduce harm from an incoming object. The phrase sounds narrow, but it contains several very different ideas. Some methods try to prevent impact by changing the object's path. Some accept that impact may occur and aim instead to reduce loss on the ground. Some depend on long warning time. Others remain useful only when time is short. The toolbox is therefore not a single machine or a single mission. It is a range of responses matched to the size of the object, the certainty of the forecast, the likely effects, and the number of years, months, or days that remain. The simplest response is not always the weakest. For small objects, or for events expected to affect a limited area, civil defense may be the most practical method. Civil defense means organized protective action on Earth rather than any attempt to alter the object in space. It includes warning the public, moving people away from the projected danger zone, protecting critical systems, preparing emergency services, and coordinating communication so that confusion does not deepen the damage. If an object is small enough that the main threat is broken glass, shock waves, local fire, or a moderate regional impact, then evacuation and shelter may save many lives even when the object itself cannot be stopped. In those cases, knowledge matters more than force. This truth is easy to overlook because space technology draws more attention than emergency planning. Yet impact consequences unfold on Earth, among populations, roads, hospitals, power systems, water supplies, and communication networks. A body that explodes in the atmosphere above a remote place and a body of the same size above a crowded city do not produce the same human outcome. Civil defense addresses this difference directly. It treats an asteroid warning as a practical hazard problem much like other natural disasters, even though the cause comes from space rather than weather or geology. This is not an admission of failure. It is recognition that not every threat requires or permits a spacecraft solution. For larger objects, or for smaller objects found far enough in advance, attention turns to deflection. Deflection means changing the object's orbit so that it misses Earth. The crucial point is that only a very small change in speed may be needed if it is applied early enough. Over years, a tiny alteration can grow into a large separation because the asteroid arrives at the crossing point a little earlier or a little later than Earth does. In planetary defense, time acts like leverage. A small push delivered decades in advance may matter more than a far stronger push attempted shortly before impact. This is why detection and response cannot be separated. The best mitigation method often depends less on absolute power than on how soon the threat is recognized. One proposed method is the kinetic impactor. This is a spacecraft that collides with the asteroid at high speed to transfer momentum, meaning motion carried by mass and velocity. The idea does not require explosive force on contact. It relies on direct physical impact and, in some cases, on the extra recoil produced when material is blasted away from the asteroid after the collision. The method is conceptually simple, though the real engineering is demanding. The spacecraft must reach the target, navigate with great precision, and strike in a way that changes the orbit by a measurable amount. Its success depends not only on the mass and speed of the spacecraft, but also on the asteroid's structure and the direction of the impact. Another proposed method is the gravity tractor. In this concept, a spacecraft hovers near the asteroid for a long time without touching it. The spacecraft's own gravity, though weak, gently pulls on the asteroid while the spacecraft uses thrust to hold its position. Over a long period, this steady tiny attraction can shift the asteroid's motion. The method is elegant because it does not depend on the asteroid's surface strength in the same way a collision does. It is also slow and requires long warning time. Its usefulness therefore belongs mainly to situations where the threat is discovered early and the needed change is small. Scientists also study methods that use explosions, especially nuclear explosive devices, though these are treated with caution because the technical and political consequences are profound. A nuclear device might be used near an asteroid to heat and vaporize part of its surface, creating a push from escaping material. In more extreme discussion, it may also be considered as a last effort to disrupt a body. Yet disruption is not the same as safe deflection. Breaking one object into many large fragments could reduce danger in some cases or worsen it in others, depending on size, timing, and geometry. Observations indicate that this method may have value in certain severe scenarios, especially for large objects found late, but it remains uncertain how reliably a real threatening body would respond because asteroid structures vary widely. Other ideas appear in scientific study as well. Focused energy, surface mass drivers, and attached propulsion systems have all been examined in principle. These concepts attempt to change an asteroid's motion by heating material off the surface, ejecting mass in a controlled direction, or pushing continuously over time. They show how broad the field of planetary defense has become. Even so, many remain less mature than the more established approaches. The difference between an interesting idea and a usable defense lies in testing, engineering readiness, launch capability, mission timing, and confidence in the physical response of the asteroid itself. This brings the toolbox back to one persistent limit. No mitigation method exists in isolation from the nature of the target. A solid metallic body may react differently from a fractured stony one. A loose rubble pile may absorb force, shift internally, or throw off ejector in ways that are difficult to predict. A spinning asteroid introduces additional complications, as does a binary system in which one body circles another. The same method cannot be assumed to work identically in all cases. Planetary defense therefore requires not only a tool, but also knowledge of the object to which the tool is applied. In practice, the strongest defense is layered. Discovery provides warning. Tracking refines the orbit. Physical observations estimate size, composition, and structure. Civil defense remains available if impact cannot be prevented, or if the object is small enough that ground measures are more sensible than a space mission. Deflection becomes possible when time, launch capacity, and knowledge align. The toolbox is broad because nature presents more than one kind of threat, and because no single response fits every combination of size, material, path, and warning time. At this level, before attention narrows to the physics of one chosen method, and before any single asteroid becomes the focus of a mission, planetary defense is best understood as a disciplined balance between knowledge and action. It is the effort to match the right response to the right object at the right time, using whatever combination of preparation, prediction, and intervention the situation allows. The idea of moving an asteroid begins with the simple physical truth. Every body in motion carries momentum, which is the quantity of motion set by mass and speed together. A moving spacecraft carries momentum. A moving asteroid carries momentum as well. When two bodies collide, momentum is exchanged according to the laws of motion. If a spacecraft strikes an asteroid, even though the spacecraft is much smaller, it can still change the asteroid's speed by a tiny amount. That tiny amount is the heart of the kinetic impact method. Planetary defense does not require a dramatic shove. It requires precise change, small in the moment but meaningful over time. This method is often easier to understand if Earth is removed from view for a moment. In open space, an asteroid follows an orbit around the Sun. That orbit is not fixed by habit or fate. It is fixed by motion and gravity. If the asteroid's velocity changes, even slightly, the orbit changes as well. The new orbit may differ only a little from the old one, but over many months or years that small difference grows into a different position along the path. The asteroid arrives at future locations a little sooner or a little later than it otherwise would. If Earth would once have been present at the crossing point, a small timing change may be enough to prevent the meeting. In this way, kinetic impact relies less on brute force than on early correction. The spacecraft used for such a mission does not need to destroy the asteroid. In fact, destruction is not the aim. The aim is to transfer momentum cleanly and predictably enough that the object's orbit shifts in a known direction by a measurable amount. This is an important distinction. Popular imagination often links asteroid defense with explosions and fragmentation. The kinetic impact approach is quieter in principle. A solid machine, guided with care, reaches the target and collides at high speed. The spacecraft gives its own momentum to the asteroid, and the asteroid continues on a slightly altered path. Even this description is still only the first layer of the physics. A collision in space is not always a simple case of one compact body striking another and sticking. Much depends on the surface and interior of the asteroid. If the target were a perfectly solid block, the change in motion would come mainly from the spacecraft's incoming momentum. Real asteroids are more varied. Many are fractured, some are porous, meaning they contain internal empty spaces. Some may be loose accumulations of boulders, gravel, and dust held together more by weak gravity than by material strength. When a spacecraft hits such a body, the impact can excavate material and throw it outward in a spray of debris called ejecta. That outward moving ejecta carries momentum away from the asteroid. By conservation of momentum, the asteroid then receives an added recoil in the opposite direction. This recoil can matter greatly. It means the effect of the impact may exceed the direct push from the spacecraft alone. A small craft may therefore produce a larger orbital change than its own mass, and speed would suggest if the target responds by throwing out substantial material in a useful direction. Scientists describe this enhancement with a momentum multiplication factor, which is a measure of how much extra push comes from the escaping ejecta beyond the original impact itself. A value greater than 1 means the asteroid receives more total momentum change than the spacecraft directly delivers. In practical terms, the surface does part of the work. Because of this, the kinetic impact method depends on geology as much as on mechanics. The same spacecraft striking two different asteroids at the same speed may not produce the same outcome. A strong coherent surface may excavate material one way. A loose rubble pile may absorb part of the blow differently and release debris in another pattern. Grain size, porosity, surface slope, internal layering, and rotation all influence the response. Planetary defense by kinetic impact is therefore not only a problem of navigation, it is also a problem of understanding what kind of small world is being struck. Direction matters as much as force. The spacecraft must not simply hit the asteroid somewhere, it must hit in a way that changes the asteroid's orbital motion around the Sun in the desired sense. A push along the direction of travel can alter the orbital period, changing how quickly the asteroid moves around the Sun. A push in the opposite direction can do the reverse. A push sideways may tilt the orbit slightly. In a real mission, the actual geometry is more complex because the asteroid may rotate, and the collision takes place in a three-dimensional orbital setting. Still, the principle remains clear. The goal is not random disturbance. The goal is controlled alteration of motion. This requirement makes precision central to the method. The spacecraft has one decisive moment. There is no hovering and gradual adjustment as in slower proposed methods. The path must be corrected long before impact so that the spacecraft arrives at the correct place, at the correct time, With the correct relative velocity, guidance systems, onboard imaging, and autonomous navigation become essential because the target is small, dark, and moving. During the final approach, the spacecraft may need to identify the asteroid against the starfield and steer itself without human commands arriving in real time. Space is too large and signal travel too slow for last-second manual control from Earth. Scale also enters the method in a disciplined way. The change in asteroid speed caused by a kinetic impact is very small, usually measured in tiny fractions of a meter per second, or at most small meter per second levels depending on the case. By everyday standards, such a change seems almost meaningless. Yet orbital motion rewards patience. An asteroid does not need to be thrown far in one instant. It only needs to be nudged enough that, after months or years of travel, the accumulated difference in arrival time becomes large compared with Earth's size. The smaller the warning time, the larger the needed nudge. The longer the warning time, the more modest the nudge may be. There are limits to this approach. A very large asteroid discovered only shortly before impact may not be moved enough by one kinetic impactor. Multiple impacts might be needed, or another method might be considered. A loosely bound object could respond in a way that is harder to predict. A rapidly rotating body may complicate targeting and the direction of the effective push. Yet these limits do not weaken the principle itself. They define the conditions under which the method is most useful. Kinetic impact is strongest when the object is found early enough, the orbit is known well enough, and the target's physical nature is understood well enough for the response to be estimated with confidence. At its core, the method remains calm and exact. A spacecraft meets a moving asteroid. Momentum passes from one to the other. Rock and dust may leap outward, adding recoil. The asteroid's speed changes by a very small amount. Its orbit changes with it. Time then turns that minute change into growing separation. In this way, a machine built on Earth can move a small world not by overpowering it, but by meeting it at the right moment and letting the laws of motion do the rest. Among the many small bodies that travel through near-Earth space, the Didymos system offers a setting that is unusually useful for planetary defense. It is not a single asteroid moving alone. It is a binary system, meaning two bodies bound together by their own gravity while both travel around the Sun. The larger body is called Didymos. The smaller companion is called Dimorphos. Together they form a small gravitational pair, one body circling the other while the pair as a whole follows an orbit that crosses the region of the inner solar system near Earth's own path. This arrangement matters because it creates a natural laboratory in space, a place where change can be measured more clearly than it can for an isolated asteroid. Didymos itself is a near-Earth asteroid. That label describes its orbit, not its immediate danger. Its path around the Sun brings it into the neighborhood of Earth's orbit, but observations show that the system does not present an impact threat to Earth in the foreseeable future. This point is important because a planetary defense test requires realism without immediate risk. The target must resemble the kind of object that could matter one day, yet it must also be safe to study and to alter in a controlled way. The Didymos system provides that balance. It belongs to the population of near-Earth asteroids that scientists want to understand, but it does not turn the test itself into an emergency. The larger member of the pair is roughly 780 meters across, while the smaller companion is roughly 160 meters across. These are modest dimensions by planetary standards, yet they are large enough to matter scientifically, and large enough to resemble the size range that could cause serious regional damage if an object of similar scale were ever found on a collision course with Earth. At the same time, the smaller body is not so large that an experimental mission becomes impractical. The whole system therefore sits in a useful middle ground between tiny objects that are hard to study and very large objects that would be far more demanding as test targets. Binary asteroid systems are not rare curiosities. A meaningful fraction of near-Earth asteroids appear to have companions. In some cases, a fast-spinning primary body may shed material that later gathers into a small satellite. In other cases, past collisions and reaccumulation may contribute to the formation of paired bodies. Observations indicate that sunlight can slowly change the rotation of small asteroids over long periods through thermal effects, and when the spin becomes rapid enough, loose surface material may migrate or escape. Over time, such processes can help create binary systems. The details vary from case to case, and it remains uncertain exactly how each individual pair forms, but the broader pattern is clear enough. Near-Earth space contains many small gravitational partnerships, not only solitary rocks. This makes the Didymos system valuable not merely as one target, but as an example of a wider class of objects. If planetary defense is to mature beyond theory, it must reckon with real asteroid diversity. Some bodies are single and comparatively simple. Others exist in pairs, with one object revolving around another under weak gravity. That extra layer of motion changes how such systems are observed and how any intervention is measured. Instead of following only one orbit around the Sun, astronomers can also monitor the orbit of the smaller companion around the larger primary. This second motion creates a more local and more rapidly repeating clock inside the system itself. In the case of Didymos and Dimorphos, the smaller body circles the larger one in a period of a little under 12 hours before the DART impact. That short orbital time is a major advantage if the motion of the smaller companion changes even slightly. Astronomers do not need to wait years to know. They can measure repeated cycles from Earth by watching the system's brightness rise and fall as the two bodies pass in front of one another or cast shadows across one another. These variations in light are subtle, but they are detectable. In effect, the system reveals its internal timing through light alone. This means a test of asteroid deflection can be judged not only by images taken at the moment of impact, but by a continuing record visible from many telescopes afterward. The system's closeness to Earth at selected times also helps. During favourable approaches, the pair comes near enough that ground-based observations become more powerful, and radar studies can add detail to shape, rotation, and orbital geometry. A useful target for planetary defense is not simply one that exists. It is one that can be measured well before and after the experiment. The Didymos system offers repeated opportunities for such study, because its orbital motion around the Sun periodically places it in a geometry suited to observation. It becomes bright enough and close enough for a wide network of observatories to follow. This wider setting also matters because the gravitational bond between the two bodies is weak compared with the gravity of a planet. Didymos is no miniature Earth. Its companion does not orbit in a deep gravitational well. The small moonlet circles under delicate conditions where even a modest change in orbital energy can alter the period by a measurable amount. This is exactly the kind of environment that makes a deflection test practical. A spacecraft impact that would produce only a tiny and hard-to-measure change in the solar orbit of a lone asteroid can create a more obvious shift in the shorter local orbit of a moonlet around its primary. The binary structure turns subtle momentum transfer into something easier to track. At the same time, the system remains a real asteroid environment rather than an artificial one. Its components rotate, reflect sunlight irregularly, and move under the complex combined influences of their own gravity, the Sun, and subtle radiative forces. observers must account for shape, shadow, viewing angle, and timing. This realism is important. A planetary defense test gains value when it takes place under natural conditions where uncertainty still exists and measurement must still be earned. The Didymos system is therefore not a simplified classroom example. It is a genuine small body system whose usefulness comes from being measurable, not from being easy. Seen at this scale, before attention narrows to the smaller body itself or to the spacecraft that will eventually arrive, the Didymos system stands as a carefully chosen environment. It is a near-Earth binary asteroid pair, safely non-threatening, large enough to matter, close enough to observe, and structured in a way that turns orbital change into something visible from Earth. Its importance lies first in that setting. It provides the wider arena in which a planetary defense idea can be tested against the steady mechanics of a real small world system in motion. Dimorphos is small by almost any ordinary standard of astronomy. It is not a planet, not a familiar moon, and not a large asteroid. It is a minor companion moving around the larger body Didymos under weak gravity in a compact binary system. Its average size is roughly 160 meters across, though its form is not a smooth sphere with one clear diameter in every direction. It is an irregular body, shaped by accumulation, collision, and exposure to the space environment. That irregularity matters because a small world is not defined only by how wide it is. Its outline, its slopes, and the way mass is distributed through it help determine how it turns, how it holds together, and how it responds when disturbed. Seen up close, Dimorphos does not resemble a single carved stone. Its surface appears rough and uneven, with many rocks and boulders spread across the exterior. The body seems to be built less like a solid mountain and more like a gathered heap of broken material. Scientists use the term rubble pile for this kind of structure. A rubble pile asteroid is not a loose cloud drifting apart, but neither is it a single coherent block. It is a body made of many pieces, from fine grains to large boulders, held together mainly by self-gravity and by weak contacts between fragments. This means that interior spaces, fractures, and rearrangements may all exist without causing the object to break apart immediately. That weak structure follows naturally from the history of small bodies. Asteroids collide with one another over immense spans of time. Some shatter. Their fragments later gather again under gravity if their speeds are low enough. The result may be a body that remembers destruction in its very construction, rather than being one ancient intact object from center to surface. Dimorphos may be a reassembled remnant, formed from pieces that settle together after earlier breakage. Observations support this general picture for many small asteroids, though the exact interior arrangement of any one object remains difficult to know before detailed study. In the case of Dimorphos, the evidence points toward a porous and loosely consolidated interior rather than a dense monolithic core. Porosity is important here. Porosity means empty space within the body, whether in tiny gaps between grains or in larger cavities between boulders and fragments. A porous asteroid can have a lower overall density than a solid rock made of the same material. This affects not only its mass, but also how shock travels through it. In a more solid object, a sudden impact may transmit force in one pattern. In a porous rubble pile, some energy may be absorbed by crushing spaces, shifting fragments, and redistributing stress through many contact points. The body may yield, settle, or throw off material differently from a compact stone. Dimorphos therefore becomes valuable because its structure teaches that an asteroid is not merely a target in space. It is a physical system with texture, weakness, and internal complexity. Its surface adds further detail to this picture. Images and measurements indicate a landscape covered with rocks of many sizes and without broad, smooth plains. Slopes are shaped by low gravity, meaning that loose material can remain in positions that would quickly collapse on a larger world. While even gentle disturbances may shift grains and stones downslope, in such an environment, the boundary between surface and interior is not always sharp in the familiar terrestrial sense. The outer layers may be part of a deeper continuum of loosely packed material. Rotation also matters. Dimorphos does not simply sit still while circling Didymos. It rotates in a controlled relation to its orbit, presenting a repeating orientation under the influence of the larger companion's gravity. This condition is shaped by tides, not tides of water, but gravitational torques that act over long periods to influence how one body turns relative to another. In a small binary system, such effect can lead the smaller body into a stable rotational state. The exact details of its motion depend on shape and mass distribution. But the broader point is that Dimorphos is a dynamic body whose spin and orbital motion belong together. Mass distribution inside the moonlet is therefore not an abstract detail. If mass is unevenly arranged, the body may turn in a way that differs slightly from what a uniform object would do. If one region contains larger boulders or fewer empty spaces, local gravity and structural response may also differ. These variations are difficult to map directly, yet they matter because they influence how the object behaves under outside disturbance. A rubble pile does not answer force as a perfect geometric body would. It answers through its real interior, with all the irregularity accumulated across its history. This is why Dimorphos is scientifically important beyond its modest size. A small asteroid that is loose, irregular, and porous represents a broad class of near-Earth bodies more realistically than a perfectly solid block would. Planetary defense must deal with actual asteroids, not simplified ideal ones. If many hazardous bodies are structurally similar to Dimorphos, then understanding such a moonlet becomes directly useful. It helps scientists learn how momentum is transmitted, how debris may be ejected, and how a body's orbit can change when the target is not a single hard mass, but a gravitational assembly of fragments. The moonlet's position inside a binary system sharpens that usefulness. Because it orbits Didymos under weak gravity, even a small change in its motion can alter its orbital period measurably. At the same time, the response of that orbit depends on the moonlet's physical nature. A denser, more solid body might react one way. A looser, more deformable rubble pile may react another. The structure of Dimorphos therefore connects directly to the meaning of any later orbital change. The orbit is what observers can measure from afar, but the body itself is what explains why that change takes the size and form that it does. Dimorphos is not simply a small companion in the Didymos system. It is an irregular, boulder-strewn, low-gravity moonlet whose probable rubble pile structure preserves the long collision history of small bodies. Its weak cohesion, internal spaces, and uneven form make it an especially revealing object for study. In its small mass and rough surface, it carries a larger lesson. The asteroids that cross near Earth may not be compact stones waiting to be pushed like simple objects. They may instead be ancient gatherings of fragments, delicate in structure yet persistent in orbit, shaped less by strength than by gravity and time. The spacecraft called DART is built for a task that is both narrow and demanding. Its name stands for Double Asteroid Redirection Test, and the name describes the mission with unusual clarity. It is not a broad observatory meant to study many targets over many years. It is not a lander or a sample return craft. It is a purpose-built impactor, created to reach one small moonlet in a binary asteroid system and strike it with enough precision that the resulting change in motion can be measured from Earth. Every major feature of the spacecraft serves that single goal: its structure, power system, instruments, navigation, and communications are arranged around the idea of a controlled collision in deep space. In its physical form, DART is modest. It is far smaller than a crewed spacecraft and much less complex than a large interplanetary laboratory. This simplicity is part of its strength. A planetary defense test does not require a large habitat, heavy shielding, or a wide suite of sampling tools. It requires reliability, guidance, and enough mass moving at high speed to transfer momentum at impact. The spacecraft body therefore carries the systems needed to fly, steer, see, think in limited onboard ways, and remain in contact with Earth during most of the journey. It also carries large solar arrays, because electrical power is needed steadily through the cruise phase and during the increasingly demanding operations near the target. These solar arrays are important not only as power sources but as part of the mission's practical design. A spacecraft going far from Earth must generate its own electricity for onboard computers, communications, thermal control, sensors, and propulsion-related systems. DART uses two large roll-out solar arrays that unfold after launch. They provide wide collecting area without requiring the mass and rigidity of older panel designs. This keeps the spacecraft relatively light, while still giving it the power needed for navigation and instrument operation. The choice reflects a larger principle in the mission. Every kilogram matters. Enough mass must reach the target, but unnecessary mass would raise launch demands and mission cost. The spacecraft's propulsion system supports the journey and the careful shaping of its trajectory. DART does not travel in a straight line once released into space. It must perform planned maneuvers to refine its path toward the Didymos system. Small changes in speed, applied at the right times, allow the spacecraft to correct launch dispersions, adjust its arrival conditions, and line up the geometry needed for impact. These corrections require accurate knowledge of the spacecraft's position and velocity relative to the Sun, Earth, and target system. In this sense, DART's mission is not only about one final strike, it is also about months of disciplined path management before that last moment becomes possible. At the front of the spacecraft's sensing system is Draco, the Didymos reconnaissance and asteroid camera for optical navigation. This camera is the spacecraft's eye. It is not merely a scientific imager for later study. It is deeply tied to guidance. The target is small, distant, and dim for much of the approach. As DART draws nearer, Draco provides the images that allow the spacecraft and mission controllers to track the position of the asteroid system against the star field. These images grow more valuable as the target expands from a faint point into a resolved body. The camera must function under changing light conditions, increasing apparent motion and the demanding need to identify exactly which object is which inside the binary system. Because the spacecraft is headed toward a system with two bodies, navigation is more subtle than steering toward a single isolated rock. At long range, Didymos and Dimorphos appear blended together or too close to separate cleanly. Only later does the smaller moonlet become distinguishable. Yet the target is Dimorphos, not the larger primary. The spacecraft must therefore recognize the system, then the pair, then the correct member of the pair, all while closing rapidly. This is one reason DART carries Smart Nav, meaning Small Body Maneuvering Autonomous Real-Time Navigation. The name is long, but the purpose is direct. It allows the spacecraft to use images in real time to guide itself during the final phase, when the delay in radio signals between Earth and the spacecraft makes immediate human steering impractical. Autonomy becomes necessary because deep space flight combines distance with speed. Commands sent from Earth take time to arrive. Images sent back also take time to return. By the last stage of approach, the geometry changes too quickly for ground teams to drive every correction directly. The spacecraft must interpret what it sees and adjust its path on board. Smart nav processes the camera images, distinguishes the target system from background stars, and later separates the smaller moonlet from the larger primary, so that the impact remains aimed at Dimorphos. This is not independent intelligence in a general sense. It is focused machine judgment built for a specific and well-bounded task under known physical conditions. The spacecraft also carries a small companion supplied by the Italian Space Agency, called Lycia Cube. This CubeSat separates from DART before impact and follows its own nearby path. Its purpose is not to guide the main spacecraft, but to observe the event from the outside, capturing images of the ejector and the impact aftermath that DART itself cannot record because DART will cease to exist at collision. This design choice reveals something important about the mission. Even though DART is an impactor, it is also an experiment. The mission must not only change the asteroid's motion, it must also document how that change happens. A witness spacecraft therefore adds scientific value by watching the target after the moment when the impactor is gone. Thermal design and communications architecture also serve the central mission. Spacecraft electronics must remain within operational temperatures despite changing sunlight conditions and the cold background of space. Antennas must return engineering data, optical information, and status updates over great distance without consuming too much power or mass. The design is therefore an exercise in balance. DART must remain simple enough to be robust, light enough to be practical, yet capable enough to carry out exact navigation against a target little larger than a sports stadium at the decisive stage of flight. Even the absence of some systems reflects intention. DART does not need landing gear because it is not meant to survive contact. It does not need sample canisters because it will not return. It does not need elaborate robotic arms because it will not touch gently or manipulate the surface. The spacecraft is shaped by the acceptance of its own end state. It is built to function completely until the instant of impact and no farther. This gives the engineering a particular clarity. Survival after contact is not part of mission success. It is that a carefully built mass reaches a chosen small world under the right conditions, carrying with it the tools needed to ensure that the collision is deliberate, documented, and scientifically useful. As DART closes on the Didymos system, the mission narrows from a long interplanetary journey into a matter of minutes, then seconds, then single images arriving one after another. For most of its flight, this spacecraft travels through deep space guided by planned corrections and regular communication with Earth. Near the target, that PIS no longer simply to remain on course toward a distant point. It is to separate one tiny body from another. Choose the correct one, and continue steering without pause until contact. The mission becomes an exercise in disciplined narrowing, with every remaining action aimed at turning a distant binary system into one precise collision. At first, the target appears as little more than a point of light set against the far background. The camera sees what seems to be a single source because the two bodies are too close together and too small to distinguish clearly at long range. This is enough for the spacecraft to know that it is approaching the system, but not yet enough to know where the smaller moonlet lies relative to the larger primary. The field of view remains mostly stars, with the target still embedded in that quiet background. The spacecraft continues inward, correcting gently while the signal from the asteroid system grows stronger in meaning rather than in brightness alone. This is where autonomous navigation becomes essential. Radio signals between Earth and the spacecraft require time to travel. During the last phase, the geometry changes too quickly for ground teams to inspect every image, decide on every correction, and transmit each steering command in time. The spacecraft therefore relies on the guidance logic carried on board. It compares what the camera sees with the expected pattern of the target system and the surrounding stars. It rejects the fixed background and follows the moving bodies. In effect, the spacecraft must interpret the scene for itself within the narrow limits of the problem it is built to solve. It does not think broadly, it thinks only toward impact. As the distance falls, the single point begins to separate into the known pair. Didymos, the larger body, dominates the view at first. Dimorphos remains the more difficult target because it is smaller and lies close beside the brighter, larger companion. The guidance system must avoid the simpler mistake of steering into the primary. The whole mission depends on striking the moonlet. The final approach, therefore, becomes a kind of visual sorting under pressure. One body is larger and easier to see. The other is smaller but scientifically essential. This spacecraft keeps refining its path so that the smaller object, once resolved, becomes the center of the closing geometry. The camera images gain detail steadily. What begins as a point becomes a shape. What begins as a shape becomes an uneven body with light and shadow across its surface. The approach no longer concerns abstract orbit lines alone. It becomes a real encounter with rock in sunlight. Didymos passes from being an entry in a catalogue to being a visible small world. And Dimorphos, once just the required target, emerges as a separate rough moonlet with its own outline. The spacecraft now closes so quickly that every new image carries far more information than the last, and each image leaves less time for change. During these final minutes, the mission is both calm and irreversible. There is no breaking into orbit and no attempt to hover. DART is committed to contact. Its guidance system uses the incoming images to keep adjusting the line of approach. Small thruster firings shape the last corrections. The spacecraft's solar arrays and body continue forward as one united mass, and the camera keeps returning the view to Earth while there is still time for the signal to cross the empty distance. Observers on Earth do not see the event live in the ordinary sense. They see it delayed by the travel time of light and radio, yet the sequence of images still feels immediate because it shows a machine moving with unwavering purpose toward a body that grows larger from frame to frame. Dimorphos now fills more of the field. Its irregularity becomes unmistakable. The moonlet is not smooth. It does not present a neat circular face. Boulders and rough ground appear, and the changing shadows across the surface make the closing speed more vivid than any number alone can do. This is not the image of an abstract target. It is the image of a small natural body with a history written into its uneven terrain. The spacecraft keeps coming. The apparent motion across the final images increases. The distance shrinks from tens of kilometers to only a few. Time is now counted in the interval between frames. The remarkable feature of this phase is how little room remains for uncertainty. Earlier in the mission, there is space for correction spread across days and weeks. Now all of that work is compressed into the success of the last guidance loop. The spacecraft must distinguish Dimorphos from Didymos correctly, keep the moonlet centered, and continue the collision path without drifting aside. At the same time, the communication system continues to send the camera data home. The world watches a sequence of images that are not symbolic representations, but the actual visual record of a machine about to strike a small asteroid on purpose. The last complete images come from only a short distance away. Dimorphos fills the frame so fully that the wider context of the binary system disappears. There is no longer a pair in view, only the local face of the moonlet itself. Surface texture dominates everything. Ridges, shadows, rough blocks, and the irregular brightness of sunlit stone occupy nearly the whole image. The target is now so close that the concept of navigation becomes almost inseparable from the concept of impact. Steering and arrival have become the same act. Then the sequence reaches its final stage. One more image begins transmission as the spacecraft closes the last few kilometers. The spacecraft is still doing its work, still seeing, still sending, but it is now entering the final second of its existence as an intact vehicle. Because the signal must be transmitted while the spacecraft is already at the point of collision, the last frame reaches Earth incomplete. Part of the image is sent. The rest is lost to the moment of contact itself. The partial picture is not an error in mission design. It is the visible sign that the spacecraft continues operating until impact interrupts the transmission. At collision, the guidance problem ends. The spacecraft's mass and speed are delivered directly into Dimorphos. The machine that crossed interplanetary space ceases to exist as a spacecraft and becomes part of the physical event it is built to create. No landing follows. No survival sequence begins. The mission's final success lies exactly in that disappearance. DART completes its purpose not by remaining, but by arriving. In those last moments, the long preparation of the mission resolves into a single clean fact: a human-built craft, guided across deep space and through the closing complexity of a binary asteroid system, reaches the intended moonlet and strikes it deliberately. The final approach becomes contact, and contact becomes the completed act of planetary defense testing. When DART reaches Dimorphos, the mission changes from guided motion to material response. Up to the moment of contact, the central facts are trajectory, navigation, and timing. At contact, the central facts become rock, dust, speed, pressure, and recoil. The spacecraft does not press gently into the surface. It arrives fast enough that the collision behaves like a sudden release of concentrated energy in a very small place. The front of the spacecraft meets the asteroid. The structure of the spacecraft collapses, and its motion begins to transfer into the body of Dimorphos and into the material blasted outward from the point of impact. In that instant, the event stops being primarily about the machine and becomes primarily about the asteroid's response. The first response is shock. A strong pressure wave travels into the surface and through the near subsurface of the moonlet. On a larger world with strong gravity and a more coherent crust, such a shock might carve a crater in ways familiar from laboratory scaling and from planetary surfaces elsewhere. On a small rubble pile asteroid, the situation is subtler. Dimorphos is weakly bound, irregular, and likely porous. This means some of the collision energy goes into fracturing rock, shifting grains, opening or crushing internal spaces, and accelerating fragments away from the surface. The asteroid does not answer as a single hard block would. It answers through its looseness and its accumulated damage. As the shock moves through the surface layers, material near the impact point is excavated and launched outward. Fine dust, small stones, and larger fragments leave the body in a spreading cloud. This cloud is called ejecta. The word is simple, but it describes a rich physical process. Ejecta is not a smooth mist leaving evenly in all directions. It is a mixture of particles and clumps moving at different speeds and along different paths. Some leave rapidly, some depart more slowly, some may escape the moonlet entirely, some may interact with the weak gravity of the Didymos system in more complicated ways. The cloud therefore contains information about the body itself, its shape, brightness, and evolution reflect the structure of the surface and the way the impact energy couples into the asteroid. The low gravity of Dimorphos makes this outward motion especially striking. On Earth, excavated material from an impact is quickly constrained by strong gravity and thick air. On Dimorphos there is no atmosphere to slow the debris, and the moonlet's gravity is too weak to hold many fast particles close. Material can rise and continue outward with relative ease. This allows the ejector plume to become broad and extended, carrying sunlight and becoming visible far beyond the immediate point of contact. The cloud is not merely local disturbance, it is the main visible expression of the impact in the moments and hours that follow. Its shape is governed by both mechanics and sunlight. At first, material leaves according to the geometry of the collision and the texture of the target. If the surface is layered, blocky, or uneven in strength, the ejector may emerge asymmetrically. If the impact angle departs from a perfectly central geometry, one side may receive more directed spray than another. After launch, the particles continue under gravity and solar radiation pressure. Very small grains respond strongly to sunlight, which can slowly push them and stretch the cloud into longer forms. Larger fragments move more by the momentum they receive at launch. Even in this early stage, the ejector plume is already a record of many scales acting together, from grain size to solar illumination. The importance of ejector in planetary defense lies not only in what it reveals, but in what it does. Every particle that leaves Dimorphos carries momentum away from the moonlet. Momentum must be conserved. If rock and dust are thrown outward in one direction, the body that ejects them receives a recoil in the opposite direction. This recoil adds to the direct push delivered by the spacecraft itself. In effect, the asteroid becomes part of its own deflection. The impactor supplies the initial strike, but the escaping material multiplies the result by acting like a natural exhaust. A loose surface that releases a substantial plume can therefore produce a larger overall change in motion than a simple impact into a body that gives off little ejector. This is why the physical nature of Dimorphos matters so much. A porous rubble pile may absorb part of the shock, yet it may also release a large amount of material because so much of its surface and near surface consists of weakly bound fragments. The collision can mobilize this material efficiently, allowing recoil to build through the outward movement of dust and stones. A denser and more coherent target might respond with a different balance between crushing, cracking, and excavation. Dimorphos shows that weakness does not mean irrelevance. Weakness can make a target more responsive in the specific sense that it allows a single impact to throw off a larger mass of ejector than a harder body might under the same conditions. The visual aftermath supports this interpretation. Instead of a brief and modest burst fading quickly, the impact produces an expansive plume with fine structure, indicating that a great deal of material has been launched. The brightness of the cloud does not come from the spacecraft itself. DART is too small to create such a visible extended feature through its own mass alone. The cloud is bright because the asteroid contributes enormous amounts of sunlit dust and debris. This means the event is not best understood as a small machine disappearing into a rock. It is better understood as a small machine triggering a much larger material response from the moonlit surface. At the crater scale, the precise form of the disturbed region is harder to know immediately because the surface becomes hidden by its own expanding debris. Yet the general outcome is clear. The impact reshapes the local ground, excavates fresh material, and redistributes loose fragments. Some material departs at speed. Some may rise and later settle elsewhere if it remains gravitationally bound to the system. Some may leave permanently. The surface after impact is therefore not the same surface that existed moments before. It is a freshly disturbed terrain whose new state is tied directly to the plume that escapes from it. The event also illustrates the difference between energy and consequence on a small body. DART carries far less energy than the impacts that form giant craters on planets. Yet on Dimorphos the local consequences are profound because the moonlet is small, weak, and lightly bound. The spacecraft's arrival sends pressure into the moonlet and sends debris away from it. Dust and rock bloom outward into sunlight. The asteroid answers by recoiling. Material leaves. Momentum remains balanced. The visible cloud and the invisible shift in motion are two parts of the same physical act. The dust, the fragments, and the recoil together show how a collision can become more than a blow. It can become a multiplied push delivered by the asteroid's own escaping surface. After the impact, the essential question is no longer whether DART reaches Dimorphos. That question is already settled by contact. The new question is quieter and more exact. It asks how astronomers can tell whether the moonlet's orbit around Didymos has changed, and by how much. The answer does not come from looking for a dramatic displacement in the sky. The Didymos system is too small and too distant for such a simple visual test from Earth. Instead, the answer comes from repeated timing. It comes from treating the binary system as a natural clock, and then reading how that clock begins to run differently after the collision. Before impact, astronomers already know that Dimorphos circles Didymos in a regular period of a little under 12 hours. This repeated motion creates a predictable pattern in the light received from the system. Because the two bodies move around one another, their combined brightness changes slightly as seen from Earth. At some times one body partly blocks the other. At some times one casts a shadow across the other. At some times the shapes and reflective surfaces present a different total area toward the observer. These changes are small, but they recur in a repeating cycle tied to the moonlet's orbit. By measuring this cycle carefully over many rotations, astronomers establish the pre-impact timing of the system with useful precision. This method belongs to photometry, which is the measurement of brightness. In the case of Didymos and Dimorphos, photometry becomes a way of tracking motion indirectly. The telescopes do not need to resolve every detail of the two bodies as separate disks. They only need to measure the slight rise and fall of light as the geometry of the binary changes. When enough observations are gathered, the repeating dips and variations reveal the orbital period. This is why the Didymos system is so useful for a planetary defense test. Its internal motion leaves a readable signal in light, and that signal can be compared before and after the impact. Immediately after DART strikes, the task becomes more complicated because the system is surrounded by ejecta. Dust and debris brighten the area and disturb the clean light pattern that astronomers rely on. The binary clock is still there, but for a time it is obscured by the cloud created by the collision. Observers must therefore continue patiently, rather than expect a quick, simple answer from the first night alone. The plume evolves, fine particles spread, sunlight acts on the dust, and the apparent brightness of the whole system changes for reasons that are not directly tied to the moonlet's orbital timing. Measurement in this stage requires caution. A single brightening or fading cannot be mistaken for a change in the orbit itself. As the ejecta thins and the system settles into a more interpretable state, the light curve becomes clearer again. A light curve is the recorded change in brightness over time. Astronomers compare the new curve with the older one and search for the repeating events that mark the mutual orbit. The key is not one dip alone, but the interval between many similar events. If Dimorphos now circles Didymos in less time than before, the pattern returns sooner. If it takes longer, the pattern returns later. The impact need not move the moonlet by a visibly large distance in the sky. It only needs to alter the timing enough that the cycle of brightness changes begins to drift relative to the older schedule. This drift is measurable because many telescopes join the effort. No single observatory must carry the whole burden. Observers at different longitudes follow the system across different parts of the day and night, reducing gaps in the record. Large professional observatories contribute precision. Smaller facilities add useful coverage. Radar observations, when geometry permits, help refine the physical picture of the system. Space telescopes also contribute by watching the ejecta and by extending the observational record above Earth's atmosphere. Together, these measurements create a shared international dataset. The changed orbit is not inferred from one instrument's impression. It is established through agreement across many independent observations. The result is clear. Dimorphos no longer follows the same orbital period it had before the impact. Its circuit around Didymos becomes shorter by a substantial margin, on the order of tens of minutes rather than seconds. This matters because the mission is designed to produce a measurable deflection, not merely a theoretical one. The shortening of the period shows that the moonlet is now moving in a slightly different orbital state around the primary. The change is large enough to be unmistakable, and far larger than the minimum success threshold set before the mission, in planetary defense terms. This is the moment when a concept becomes demonstrated reality. A human-built spacecraft has not merely hit a small world, it has altered that world's motion in a way that telescopes can verify. Yet the measurement does more than confirm success. It also begins to explain the physics of the impact. If the period had changed only by the amount expected from the spacecraft's direct momentum alone, one conclusion would follow about the target's response. The larger observed change indicates that ejecta recoil contributes significantly. In other words, the escaping debris adds extra push. This turns the orbit measurement into a diagnostic tool. By reading the new period, scientists can work backward toward the efficiency of momentum transfer. The binary clock not only says that the moonlet moves differently, it helps reveal why the change reaches the size it does. Further study refines this understanding. The orbit of Dimorphos is not described by one number alone. Shape, rotation, mass distribution, and the exact geometry of the mutual motion all influence how the light curve appears. After impact, astronomers therefore continue modeling the system in detail. They test different physical assumptions against the observed timings. They ask how the disturbed shape of the moonlet, the distribution of ejecta, and the gravitational relation between the two bodies all contribute to the new orbital behavior. The answer becomes richer than a simple before and after comparison. It becomes a small body dynamics problem grounded in real data. The changed orbit also becomes a foundation for later missions and later interpretation. A deflection test is useful only if it leaves behind knowledge that can be applied elsewhere. In this case, the measured period change-links observation to response. It shows how a rubble pile moonlet in a weak binary system reacts to a high-speed kinetic impact. That does not mean every asteroid would respond identically. It means planetary defense now has one real calibration point in nature. A model once supported mainly by theory and laboratory scaling now has an actual asteroid case against which future calculations can be checked. In this region of the story, the central action is therefore one of reading rather than striking. Telescopes return night after night. Light rises and falls. Dust first confuses the pattern, then slowly yields a clearer signal. The old binary rhythm no longer fits. A new rhythm emerges. From that altered timing, astronomers recover the changed orbit and turn a brief collision into durable knowledge. The motion of Dimorphos is no longer only a path through space. It is a measured answer written in repeating light. The DART result shows that an asteroid's motion can be changed by human action. That fact is real, measured, and important. Yet the meaning of that success for Earth must be understood carefully. Dimorphos is not a city-killing asteroid on a collision course. It is not a lone body approaching Earth under urgent conditions. It is a small moonlet in a binary system chosen because its orbital change can be measured cleanly and safely. The question is therefore not whether DART solves planetary defense by itself. The question is what kind of truth DART establishes, and how that truth carries outward into the much more difficult case of a real hazardous object. The first answer is that DART proves the principle of kinetic deflection. A spacecraft can reach a small asteroid and change its motion enough for telescopes to detect the result. That alone matters because planetary defense depends on turning theory into demonstrated capability. Before DART, scientists have strong models, laboratory experiments, crater studies, and decades of orbital mechanics. After DART, they also have a full-scale asteroid case. A real target in deep space responds to a real impact with a measurable orbital shift. This gives future planning a firmer foundation. Engineers no longer work only from simulations and scaling laws. They work from one tested event in nature. At the same time, the test does not remove the larger uncertainties that surround Earth protection. A hazardous asteroid may differ from Dimorphos in size, shape, composition, structure, and spin. It may be a single coherent body rather than a rubble pile. It may be much larger. It may be much smaller, but discovered too late. It may travel alone instead of circling a larger companion. These differences matter because the success of kinetic deflection depends on the physical response of the target as much as on the accuracy of the spacecraft. DART shows that one kind of asteroid can be moved under one set of conditions. It does not show that every threatening asteroid would react in the same way. Size is especially important. Dimorphos is large enough to test a meaningful deflection, yet small enough that one spacecraft can change its local orbit by an observable amount. A much larger asteroid carries more mass and usually requires a larger momentum change to achieve the same safety margin over the same warning time. This does not mean kinetic impact becomes useless for larger bodies. It means the mission design changes. A bigger target may require a heavier spacecraft, a faster impact, multiple impactors, or a much earlier launch. Planetary defense is therefore not a matter of repeating DART exactly. It is a matter of scaling the idea to the body that is actually found. Warning time governs that scaling more than any other single factor. If a hazardous asteroid is discovered decades before a possible impact, even a tiny change in speed can grow into a large missed distance by the time Earth reaches the crossing point. In that case, a kinetic impactor may be enough, especially if the object is not extremely large. If discovery comes only a few years before impact, the required change grows larger. If it comes only months before impact, the mission becomes far more difficult or impossible. In that sense, DART works for Earth only when Earth first works for DART, meaning when detection, orbit refinement, and decision-making happen early enough that a modest physical push can matter. This is why real planetary defense begins before launch. It begins with surveys, follow-up observations, and orbit determination. A spacecraft cannot be sent wisely toward a hazard that is poorly known. Before any deflection mission, scientists need the best possible understanding of the asteroid's path and its physical nature. If the orbit still carries large uncertainty, a mission could be aimed at the wrong place in time. If the asteroid's structure remains unknown, the expected momentum transfer may be misjudged. DART benefits from careful target selection and long preparation. A real defense mission would need even more. Saving Earth is not simply an engineering problem of impact. It is an information problem first. This leads to the need for reconnaissance. In some scenarios, a threatening asteroid might justify a first mission whose main purpose is observation rather than deflection. Such a mission could measure shape, mass, rotation, surface texture, and perhaps the internal response to subtle forces. This knowledge would guide any later attempt to move the body. Mission planning must also include direction, not only force. A hazardous asteroid must be pushed in a way that changes its future arrival relative to Earth in the desired sense. The aim is not simply to strike it somewhere. The aim is to alter the orbit usefully and predictably. This demands precise launch windows, cruise corrections, and final targeting. There is also the question of how much confidence is enough. DART demonstrates a measurable outcome under favourable test conditions, but Earth protection requires decisions under uncertainty. A hazardous asteroid might have an impact probability that changes as new observations arrive. Its size estimate might narrow only gradually. Its physical class might remain partly uncertain, even close to launch. Decision-makers must therefore act within ranges of knowledge rather than perfect certainty.